Hey, I'm Adriana.
I'm Tin.
And I'm Travis.
And this is our Steganography project. I hope y'all enjoy it.
See this image? Looks like a regular dog, right? Well, it's not. There's a hidden image. How are we doing this, you ask? Well, hold on, bucko.
Image stores numerical values in a three-dimensional matrix that consists of three layers: the red layer, the green layer, and the blue layer. Based on the intensity of each color present in the current pixel, a number value between 0 and 255 is assigned to each layer. The final red, green, blue triplet determines the color of the pixel. In our image here, we have a 2x2 matrix which corresponds to 4 different pixels. Our embedding techniques use 8-bit representations of numbers. An 8-bit representation of a number has 8 spots, each filled with either a 0 or a 1. A 1 means that the slot is turned on, and a 0 means that it's turned off. Each slot has a different value of 2 to the n. The n is determined by the position of the slot. The first slot has an n of 7, the second has an n of 6, all the way down to an n of 0. Here we have the bit representation of a 5. Every spot where there's a 1, we sum the 2 to the n for that spot. So for 5 we get a 1 here, so we get a 2 squared, and a 1 here, which gives us a 2 to the 0 power. 2 squared plus 2 to the 0 is 5.
First, we use a flatten function to convert the secret image into black and white. If a value in a given pixel in the secret image is above 127, the corresponding pixel in the flattened image is 1, which is completely black. If the pixel in the secret image is 127 or lower, the corresponding pixel will be 0, which is completely white. This flattened image will then be hidden into the colored dog picture. One of the embedding techniques we will be using is the odd-even technique. This technique can be applied to the red, green, or blue channel, so it can be used to hide up to 3 images. Let's say we're working in the red channel. This technique works by going through each pixel in the black and white image. If a pixel is white or 0, the corresponding pixel in the red channel of the dog image is made even by adding 1 or 0. If a pixel in the black and white image is black or 1, the corresponding pixel in the red channel is made odd by subtracting 1 or 0. To recover the hidden image, we simply work backwards. The recovery function starts by making a blank image. Then it goes through each pixel of the red channel of the dog image. If a pixel is even, the corresponding pixel in the blank image is white. If a pixel is odd, the corresponding pixel will be made black.
Our second embedding technique is called bit to embed. The name is pretty straightforward in regards to what it does. It embeds the image that we want to hide into the second bit of an image using the bit get function. In our case, we use this to embed the 3 images into the second bit of the dog image. 1 image is embedded into the red layer, 1 in the green, and 1 in the blue. Our function allows us to choose the image we want to embed, choose the image we want to embed the hidden image into, which in our case is dog image, and the letter C is representative of which of the 3 layers we want to embed the image into. A loop allows us to go through values of both images. We specify what bit we want to look at using the bit get function. The bit get function simply looks at values of the user-specified bit of a chosen image. This is implemented into our solution by looking at the second bit of dog image, which is the image we want to embed the secret image into. We look at the flattened image that we want to embed. If the value of a pixel is 0 or white, it replaces the corresponding value of the second bit of dog image to a value of 0. If it is already 0, it leaves it as is. If the value of the pixel in the image we want to embed is 1 or black, it replaces the corresponding value of the second bit of dog image to a value of 1. After this process, the function returns a new image with the embedded image. The same process is repeated for the bit3 embed and the bit4 embed functions. The only difference is that in the bit3 embed function, we are embedding an image into the third bit, and in the bit4 embed function, we are embedding an image into the fourth bit. The recovery for the bit 2, 3, and 4 embedding techniques uses the bit.get function again to look at the specified bit of the image we embedded the images into, and it copies these values onto a blank image, and that returns the recovered image.
The expand function to display the hidden image after the embedded image has been recovered. The expand takes a matrix of ones and zeros, and any value of 1 that adds 254 and makes it to a 255. Then by changing the color map to the grayscale, any value that is 255 comes out as black, and any value of 0 comes out as white.
Now onto the demonstration of our guided user interface. So here is our full code, which includes all of the functions that were previously stated in this video. When we run this, we get our guided user interface, which allows us to select the image that we want all the images embedded into. From here, we choose a hidden image that we want to embed into that image. Then we use an embedding type, load the embedded image, and use the corresponding recovery type. This was a demonstration to show that we can do this with an image. Now we will do this with the remaining 9 images to show that our code is capable of hiding the 10 images into one image. So the way we're doing this is, again, we're loading the embedded image, hiding another image within that, using an embedding type, and then saving that new embedded image and repeating the process over and over again until all 10 images are embedded within the embedded image. Embedding types 1 through 3 correspond to the odd-even embed. Embed types 4 through 6 correspond to bit 2 embed. 7 through 9 correspond to bit 3 embed. And embed type 10 corresponds to the bit 4 embed. Now we save the embedded image, which holds the remaining 9 hidden images, one more time. We load that embedded image and proceed to use any other recovery types. If you use recovery type 5, for example, the image you receive will be the image that you embedded with embedding type 5. You can recover the images in any order.